appreciate getting a chance to be here today. I've learned a lot about extrusions and other parts here. And let's back up one. What I want to talk about is the coatings and the surface treatment to the medical devices. I was talking about just some of the challenging things in extrusions. There's also challenges in coatings. Specifically, I want to talk about today about coating metals and then the inner diameter of actually catheters. A little bit about me. I was fortunate to start my career at one of the original neurovascular companies, Target Therapeutics, which is now Stryker Neurovascular. So watching sort of the growth of this has been a pleasure throughout these years. Joined Surmodics, so I lived up here in Eden Prairie for about 16 years, and various R&D roles there on coatings. And then moved to, for Southern Research, some early medical development with them and UAB. But then about 6 years ago, returned to the roots of coating and joined BioCoat and been there since then. So BioCoat is basically we focus on hydrogels. So we have that full service solution. We make the coating products, these hydrophilic coatings that can be applied to the devices. We can also then do the coating service for that. So if you don't want to coat it at your facility, call us and we can coat those for you. The other part is we also make custom hydrogels. There's a company we've purchased over in Europe that makes custom hydrogels for things that are not necessarily coatings, but like for use for contact lenses and things like that. So I want to kind of focus on the coatings today. And so what we coat, we literally go from head to toe. We have things up in the head, the neurovascular, peripheral vascular, cardiovascular, even outside the body of microfluidics and thin films. But all these require binding that coating to the surface and making sure it stays on there well. So I want to start with just what are the benefits of lubricity for medical devices? And it's not just the benefits. I would argue that there's actually almost a critical need for those. And as part of your design requirements for the devices. Dr. Gupta talked about the tortuosity and the getting to the site. We can have these wonderful devices, and if you can't get to the site, nothing really matters. You have to be able to get to there, and a lot of that is built up on the friction. You notice on the body, there's very few straight paths in the body and the vasculature. There's a lot of twists and turns. So improving that ease of access for those devices, and in fact, sometimes it can even enable, he talked about the growth in the stents. Part of the growth when all those companies were duking it out for this was actually some of the deliverability of those, not necessarily the stent design, but as well as how you can get to the heart to treat those. It can even enhance the device functionality. I think some of the best examples of that are in the neuro field where these aspiration catheters are getting further and further into head, and that's because they can get to that site, and that is minimizing the friction all the way from the groin or the radial access up into the head, minimizing that to get there to actually pull those clots out. With all that, as you're sliding those throughout the vessels, it can minimize or eliminate the trauma by minimizing the friction building up in those vessels. All this talking about, sort of the drive-by stenting, as Dr. Gupta kind of talked about it, but it really can even shorten the procedure time within those devices. I mean, I remember when I was first rolling out the hydrophilic coating catheters at Target Therapeutics, and the doctors' just eyes kind of popped open at just how quickly they would get to those sites. Shaving time off of there helps the patient. You don't have as much radiation exposure, anesthesia. But even the OR staff, I mean, they're wearing these lead gowns. That's heavy, and there's radiation exposure, and then just freeing up the room to kind of do for the next patient. So let's talk about some of the strategies to reduce friction. Certainly, you can start with the choice materials. We've heard about PTFE, which is sort of an inherently lubricious material, but there's also some limitations on that in terms of its structural properties. HDPE also can have some lubricious characteristics. But then you get into some of your high-performance materials, the PBAXs, polyurethanes, very tough, nice and soft, but kind of tacky. So then you have to what else can you do to kind of minimize that friction? We talked about with the extrusion one about adding in some of these additives, Propel, Mobilize, that can reduce the friction a bit. I'll show some data on how well it does that. But then to really kind of separate out sort of those physical properties of what your extrusion, your device is, as well as on the surface properties, you need a coating. Clearly there's PTFE coatings, there's silicone oil, and then there's the ones that are sort of near and dear to my heart, which are the hydrophilic coatings that really, and again, we're in Minnesota, so it's like, if you're ice skating, you're gliding on a layer of water. That's exactly what's going on with these. You're trapping the water on that gel, and that allows that device to really kind of zoom through the arteries, minimizing the friction. I'll just give a little bit about how we evaluate the lubricity so that when you see the data, you know what we're doing. There's kind of two ways. We have just a vertical pad test where we just take two rubber pads, squeeze them together, pull the device up and down while hydrated. What I like about this, it allows you to have a direct comparison of different surfaces without kind of separating out the device design. For us, we use silicone pads. If we really want to get crazy, we do Delrin pads and apply 500 grams of force. And then to show the durability of that, you can cycle it multiple times. Ideally, it's not changing over that time, which is, again, you have that same feel that the physician has throughout the course of the procedure. You can also look at tortuous paths, where you're kind of combining the device and the coating, which is more of your track testing that you all are when you're developing the devices. Also needs to do that for like when I'm going to talk about some inner diameter coatings, that it's really tough to kind of do that, just sort of squeezing the pads together. This is an example of sort of just the order of magnitude friction reduction of these different strategies that I talked about. So, over on the right-hand side, these are the ones, those additives, those Propel and Mobilize from a PBAX. We're keeping in mind, we're putting 500 grams on here, so you're kind of cutting it in half, and that's similar to what those the literature says about those materials, reducing that friction by a bit. But Teflon reduces even further, and silicone oils. But if you really want to kind of reduce the friction down, like a 95% reduction in friction or more, you need those hydrophilic coatings. And this is an example of you're down at under 20 grams, and we're applying 500 grams on there. So really, kind of it's a sort of a jump from all the other ways of reducing that friction. The other piece of this evaluation is you've got your lubricity, you want to make sure you have your durability, but there's this other part that the regulatory agencies are about particulates. I can go on for probably 20 minutes just on this. I promise I won't. But just say that the regulatory agencies are asking about this, about the test results, and actually the justification of this. And the challenge for all of us is that there's all sorts of factors that can contribute to particulate generation. It's not just the hydrophilic coating. There are standards and guidance. I got 4 of them listed down there at the bottom. And not one of them tells you exactly, if you do this and get this result, you're good. So there's judgment that we're there. There's negotiations with the FDA. It's a challenge. But if you can reduce the number of particles, you're probably in a better spot than if you have one that's high. I'm just going to show just one example of this, of kind of putting this perspective and kind of opening up a different dimension when you're evaluating these coatings. This was 7 on-the-market neurovascular catheters that we purchased. 3 of them actually had BioCoats coating on them, and then 4 other ones did not. That graph on the left, that's your typical, well, let's see how good the coating and the trackability is. And you can see that for the vast majority of them, they're reducing the friction quite well. Around 10 grams, 15 grams of force. With the exception of one of them, they actually have pretty good durability. They don't change much over that time. There's that number 7 that the coating seemed to kind of be coming off. But you look at the other side, the particulate evaluation here. There's a huge difference, the amount of particles coming off. Now, I'll say all these are on the market, so but there's a big difference here. Setting aside number 7, which was the one where it'd be the coating coming off, a 10-fold difference. This is the part there, the challenge of what's good, what's bad. But again, if you can have a low particulate and the good durability, probably want to go with that way. But that's just sort of part about how we evaluate these coatings. There's a little bit of talk about PTFE today, and manufacturers are phasing out these PFAS-containing materials. This has been causing all sorts of supply chain disruptions. Somebody talked about qualifying that second source and taking potentially some years to do that. Hasn't happened yet, but certainly the European Chemical Agency is proposing an EU-wide ban for all PFAS materials, which will have huge implications for PTFE materials. So we have to, looking at some alternatives for those. Have been working through those PTFE liner availability, and several of the companies here have been helping to contribute to minimizing that supply chain issue, but that, again, that's also been an issue. One that was sort of mentioned briefly is that PTFE doesn't do very well on irradiation sterilization. So if trying to move from ETO to one of these other ones, PTFE will kind of turn to dust, and so needing some alternatives for those. So what I want to kind of show a little bit about some alternatives on the coatings, hydrophilic coatings that could, where you typically would use a PTFE. The other piece on this is, on the particulates, which I kind of talked about before, is it's not just hydrogels. So this was a study done down at Mayo Clinic, where they actually looked at thrombectomy devices. They actually pulled the clots out, sectioned them, and then looked at the amount of foreign material left in those clots, which was really kind of interesting that half of all their clots they pulled out had some sort of foreign material in it. What the really interesting part was about 90% of them, so pretty much all of those that had foreign material had PTFE in it. Only 30% of them had hydrophilic coating. So again, it's the entire totality of all your devices as well as the OR part on there. But that, that part is also PTFE is coming off, which makes sense as you're running a guide wire and a catheter through there. So let's talk about some challenging surfaces for this. The first one I want to talk about is metals. And for those, it's, metals are non-reactive. For a lot of times with these coatings, they can kind of bind to a polymer surface. The metals, you really don't have that option for. Metals are, incredibly incompressible by design, and so that, versus a catheter maybe has a little compressibility. This one on a guide wire or something like that, nothing's moving on there, and so you're really stressing the coating for those. Guide wires, of course, are extremely narrow. I mean, sort of, anyone seen, on things, a cheese cutter? I mean, it's the same concept. You put that down there, you're going to slice through there. If you've got that hydrogel, it can really stress there. And then by applying that coating on, you can potentially stiffen the hypotubes or the coils that these metals are using. And then, of course, how do you evaluate and the performance testing? Current strategies, of course, are to apply a coating onto those. You put an extrusion over wire and then put the coating on. So essentially, you're putting a plastic surface on there and then put your coating. This requires a separate primer application, which parylene, silanes. You have to use an oven, a vacuum deposition. So it's an additional step and potentially some additional thickness for there. Or non-hydrophilic ways. Again, a PTFE spray, silicone oil. And I'll just say silicone oil and hydrophilic coatings do not mix, so I want that in the next zip code if you're doing that. So a little bit about what we've done for coatings for metals. We have a two-layer system. Our base layer is actually not hydrophilic, but it's very adhesive, and it can stick directly to the metal without any additional primers for there. So we can do stainless steel, we can do nitinol, we can do platinum for those. Our hydrophilic layer, which actually absorbs the water, is bound to that base layer, and you get that exceptional friction reduction and durability, the same as we're seeing with the catheters for those. Again, we're not needing an additional primer layer, so you can just say apply the hydrophilic coating, cure the hydrophilic coating, and we do it both in either a heat cured system or a thermal cure system. So there's some time savings and labor savings for those. I'll show some data for this just to kind of put it into comparison. So this is taking a nitinol guide wire. The one on the right there is a Trimo guide wire, and which if those who've dealt with the guide wires before knows that actually has a really good coating for that. We put that through a sort of a loop-to-loop test there and getting around 140 grams. We took that exact same wire, stripped off its cladding, put our coating on there, and got actually even lower. Now again, it's a little thinner, but but the durability was awesome as well. So we're matching what we can do that by applying the coating on to the device for that. This was nitinol at 18 thousandths. This was a different guide wire where we had a stainless steel coil and then a nitinol core coating all of that on there. And getting, you can see it stained there is it's nice and uniform for those. And then just, again, very thin, not bridging that as well. So you can get to see the stainless steel coil, the junction, and the nitinol core. The final one I want to talk about is inner diameters. And this one is a new one for us. But the challenges for coating the IDEA catheter is compared to on the outside, you don't have any sort of line of sight for curing. So how do you cure that? There's a fill and drain control. You have to kind of not only just dunk that into a dip tube or something like that, you have to kind of pull it up into there and then drain that out at a uniform way of doing there. And the diameter has a huge effect on how well you're doing this coating. The strategies, the PTFE liners are kind of the way of minimizing the friction on the inside. But if you want to put a hydrophilic coating, there's right now it's clear tubing, or I've tried to do high fiber optic curing on that, and believe me, that is not the way you want to go because it takes a huge amount of time to do that. So what we're doing is able to cure this with our heat cured system, and we're getting performance equal to or better than PTFE on the inside here. So this would allow more design flexibility for you all to design a catheter that maybe does not have that PTFE liner. What does that mean in practicality? Well, the PTFE's got a bit of a thickness there. By removing that, you can put a coating on there, which is always thinner than the liner. For an aspiration catheter, getting a larger bore, and so you're keeping the same OD, but a larger inside that you can put something bigger through there. Having softer distal tips, which improving the flexibility on there. Of course, the issue with a lot of these soft materials is they're not lubricious, and they're in fact pretty tacky. And so needing a coating to allow the catheters, guide wires on the inside to kind of flow through there. And then for the fluid dynamicists in the audience, there's part of the challenge of this is that on the larger diameters, it's actually pretty easy to kind of apply the coating in there. You want to have a certain airflow that is drying that out on that inside. On a larger diameter one, you want a certain linear flow, and I'm just using an example of 10 to say 30 miles an hour of air flowing through there. On a larger catheter, you've got a pretty wide range of the flow control. As that goes down lower and lower, you're very tight between the high and the low end that, one, it's not going so fast that it's squeegeeing off the coating, or so slow that you're actually getting clots or plugs in there. So when I talk about this, people say, well, yeah, can you coat a 1, a 2 French one? And I kind of grimace. That not saying no, I'm just saying not right now. But we can kind of get things down to around a 4 French. But this is the reason why, is that control of that at those zones it can get extremely difficult to do that. So a little bit of the data on the inner diameter coatings. What we've got here is PBAX tubing. And again, this has either Mobilize or Repel with barium sulfate in there. So it has some friction reduction. What we're taking is a Tygon tubing on the inside, so that's uncoated, sliding those two in. And as you can see, we had to be very careful not to damage our load cell when we didn't have the coating on here, that it was up around 200, 250 grams. Putting that coating on there, same material, we're dropping that down to around 25 grams. For comparison, the one on the left-hand side is a PTFE liner, and you can see where the force is from there. So we're actually getting values lower than PTFE from the coating on that on sort of a very soft material. And you heard me talk about particulates. So you're like, well, that sounds great, but how are the particulates working out in this? And the short answer is actually quite well. That in this case, what I'm showing here is actually the 3 sort of bin sizes the FDA recommends that you report your numbers on. But we have our ID-coded PBACs. There is the marketed guide catheter, which has a PTFE liner. I'm not going to say who this is. And then just a PTFE extrusion. In all 3 bin sizes, we're seeing that the particles are about the same for all of them. And again, this fits with what we're seeing with what that one paper from Mayo is that we're getting about the same number of particles here, lower friction. And then just show about the uniformity there. Again, we just coated some clear tubing for this case. But this is PBACS tubing as well as silicone tubing. So Paul, we were able to coat silicone tubing here. This is just coated on the inside and then stained through there and get the nice uniform color. Otherwise, you need to kind of maybe your typical catheter, looking at that, maybe cutting it open, and we've been able to look at it as well for the uniformity. So with this, appreciate the opportunity to talk here, but what I want to kind of get across is, friction reduction is, in my view, a critical design requirement of many medical devices. Ideally, not just coming in right at the end, oh my gosh, I need a coating, is, asking about that in utilizing that at the beginning as you're doing your design of your devices. Certainly PTFE has enhanced lubricity on the metals and the lumens, but there are some challenges with those. And if you want to try and apply a hydrophilic coating, that does even pose some even more unique challenges. But I think we've kind of worked through some of those. But in any way you're doing this on any of the coatings, you need sort of that comprehensive evaluation of looking at your friction, your durability, as also as this particulate generation, ideally not much particulate generation. So appreciate the opportunity to talk today and happy to take any questions.
Questions for Bob? I think we have one in the back. We'll get a microphone to you so we can all hear your question, especially Bob, because he has to answer it.
That's right.
Thanks. Yes, you had mentioned lubricity, and some of the cases Dr. Gupta talked about actually have multiple exchanges, right?
Mm-hmm.
And during that, the coating often dries out because of these exchanges and has to be rehydrated.
Yes.
Have you measured how many times of rehydration and what its impact is to failure on that lubricity measurement?
Right. So on the rehydration, it's coming out, sitting there, then drying out, then after rehydrating it. That part, what we've seen is if it's drying out and not really being touched during that time, you can rehydrate that. It'll be. We've seen multiple times. I mean, I've had things. The tricky part is when and it's not just ours, but most of these hydrophilic coatings, once you start drying them out, they can get a little tacky. That's the part where you can actually damage it if you're not careful.
And that's what the Terumo product does really well. I learned.
I know.
Experience.
Yeah.
And it's the seizure, the catheter freezing up with the wire is devastating in those long procedures.
Right.
So kills a product.
Yes. Saw another hand.
Oh, Steve's got one.
Yeah. Can you turn our microphone on?
Nick's got another one here for you, Gowrie.
So the coefficient of friction data that you have shown,
Yes.
is it a dry test or a wet test?
So all these were wet. Because again, the hydrophilic coatings obviously need the water there. So I'm evaluating all of them there. Understand that PTFE, silicone, probably the Propel doesn't necessarily need the water.
Yeah, okay. And you mentioned that your coating doesn't need like a primer, right?
Right.
For most of the substrates. And what is different in your chemistry compared to the other chemistry?
So on what we're doing, we have a sort of a 2-layer system that it showed, and that base layer since it's not a hydrogel, it actually it is pretty adhesive as well. It has some cross-linkers in there, which will, for plastics, will bond to that. But even without that, it actually sticks very well and won't hydrate and kind of float off for there. And then from there, we can attach on our hydrophilic topware.
Okay. And you have shown some inner diameter coating and some coefficient of friction, and I assume those are tested against the silicone and the Delrin. Have you had any data against like a PBAX or like a TPU type of a surface? See how the results looks like?
Right. So we kind of standardize on our friction with the, like on those rubber pads with the silicone rubber pads or the Delron. That's kind of what we're using. The ID data we've actually looked at running, an uncoated PBAX through there and getting, again, very good results on that. And again, typically on these, if you're putting another device in, that's going to be coated on the outside of that smaller one, so you actually get even better friction reduction.
Okay. And is there like any concerns with the sterilization or like multiple reusing of these coatings in the end application?
So on the sterilization, nice thing, no. I mean, we've shown ours. I mean, again, ETO, E-beam. We're just even looking at actually, X-ray sterilization, and they all seem to work very well with that. So I think you have quite a bit of flexibility on your sterilization choices.
Thank you.
Are there specific flavors of silicone that are more compatible with your coating?
I'm not sure what you mean by, tell me a little more about flavors of silicone.
A durometer?
Okay, yes. Yeah, I mean, the harder ones certainly are a little easier. I mean, the ones that you're, not having sort of some of the, unreacted or looser oils coming out, makes it exceedingly difficult to coat something, and not just our coating, but, on those if that's coming to the surface and coming off. So we're having probably better luck with the sort of the higher durometer silicones, but we've certainly continued to work with the low durometer ones too.
Oh, we got a question down front.
So I was curious about, you talked about that the UV cure wasn't the way to go for the ID coating. I was just curious about what tests did you do when you did your thermal cure for your ID coating to make sure that, you've got particulate is one thing, but you have just straight the coating dissolving off and coming out into the patient.
So our ID coating, we are using that thermal cure system because, again, we don't have to do the line of sight. We've been looking at this, make sure, one, the performance, making sure that it isn't wearing off. We have opened up some of those and made sure it's staining on the uniformity. And then again, we're working with customers, and they're running it through on their particular applications and are seeing a significant benefit for that coating on there versus if they didn't have it on there. And again, it opens up the design options that you don't have to have that liner or having just a little more real estate on the inside.
Is there another one here? Yep.
For your 4 French catheter coating the ID, what length were you successful in coating that?
We can do what I'd call sort of full-length catheters, 150 centimeters. The length actually isn't really for us the issue. It's as you get down smaller and smaller that there's some control, the fluid control gets a little bit more challenging.
Oh, question down front.
Quick one here. So if our engineers want to try your product, the best way is to send the samples to you and then get it coated back, or?
Yes. So I mean that's probably usually the best way is talk to us. We'll send samples. Ultimately, if you want to set up at your facility, happy to do that. But I think the first thing is to kind of dial it in with the equipment that we have before we make that investment, and at that point we can kind of talk about ultimately where it's going to be coated, whether we continue to do it or do it at your facility.
Okay, all right, thank you.
Anyone else? Going once, twice? Okay, thank you. Thank you, Bob.
All right.
Appreciate it.